Have you ever just looked at something really complex like the economy or the weather or even a population of animals and just seen chaos? It feels totally random, right? Completely unpredictable.
But what if I told you that hidden deep inside all that chaos, there's a code, a kind of mathematical language that doesn't just describe the system, it can actually predict its future? Well, today we're going to pull back that curtain and reveal the surprisingly simple code that governs survival itself.
And look, this isn't just some abstract thought experiment, right? For conservation scientists, for ecologists, this is literally a life or death question. Can we really take all the wild, random seeming ups and downs of a population and find a clear signal, a signal that tells us if that species is on the path to recovery or heading for extinction?
To see how this all works, let's you and I become wildlife biologists for the next couple of minutes. We're going to use a hypothetical bird species as our little case study. All the clues we need to predict their future are right here in front of us. We just have to learn how to read them.
All right. So first things first, every good investigation starts by gathering some intel. For our birds, this means we need to understand the basic fundamental rules that govern their lives, their rules of life, if you will.
Okay, so at first glance, these rules might seem almost too simple to be useful. In their first year, these birds are just too young to breed. But in their second year, each one has about 5 female offspring. In their third year, it's 4. Meanwhile, survival is tough. Only about 15% of the young ones even make it to year 2, and then only half of those make it to year 3. That's it. Those are the facts on the ground.
Now, you might be thinking, that's it? That's all we've got? But trust me, these 6 simple rules are everything. They are the gears and levers we're going to use to build our very own prediction engine. It's kind of like a mathematical time machine that lets us see into the future of this population, not with magic, but with math. And the cool thing is building it is actually super straightforward.
We just take our rules and get them organized. First, we lay out the birth rates for each age group. Then, we do the same for the survival rates. After that, we just assemble all these numbers into a special kind of grid. It's called a Leslie matrix, named after the biologist P.H. Leslie, who came up with this whole brilliant technique way back in 1945. And voila, here is our engine all put together.
See how it works? That top row has our birth rates. 0 for the youngsters, 5 for the second years, and 4 for the third years. And then that diagonal line just below it, that's our survival rates, a 15% chance of getting from year 1 to year 2, and a 50% chance of getting from year 2 to year 3. This simple little grid now holds the entire blueprint, the DNA of our population's future.
So, we've built our engine. Now, for the fun part, it's time to turn the key. We're going to feed it an initial population and just see what happens. This is where the magic really starts.
Let's start things off with a population of 3,000 young birds, 440 in their second year and 350 in their third. This is our starting line, our year 0. All right, here we go.
We're going to apply our engine. We multiply our matrix, which has all those rules of life baked into it, by our starting population. And that will project us forward exactly 1 year. Let's see what the future holds.
Here are the results. Whoa! Okay, so after 1 year, the number of young birds jumps up to 3,600, but the oldest birds drop to 220. Then the next year, the young birds drop while the other 2 groups go up. The numbers are bouncing all over the place. It looks completely random. It really feels like we're right back where we started, doesn't it?
But hold on, let's not give up yet. What if we keep applying our matrix, year after year after year? Let's project forward to year 3, year 9, year 20, even year 100. When we do this, something absolutely fascinating starts to emerge from all that chaos.
Look at what happens to the percentages of each age group over time. At first, they're jumping around 79%, then 84%, then 80%. But as time goes on, they start to settle down. By year 20, we see 82.06% young birds, 12.05% year 2 birds, and 5.9% year 3 birds. And here's the amazing part, these percentages stay constant from then on. Even at year 100, it's still 82.06%, 12.05%, and 5.9%. We've found the stable age distribution.
Now here's where it gets even more interesting. Let's look at how the total population changes from year to year. If we divide each year's population by the previous year's population, we get a growth factor. At first, these factors are all over the place, going from year 0 to 1, we have 4,270 divided by 3790, which is 1.127. Then from year 1 to 2, it's 3,895 divided by 4270, which is 0.912. But eventually, they converge to a single number, 1.0216. This means that once the population reaches its stable age distribution, it grows by exactly 2.16% every single year. This number, which we call lambda or, is incredibly powerful.
We can take this one step further and convert our annual growth factor into a continuous growth rate, just like you'd see in exponential growth formulas. Since our population grows by a factor of 1.0216 each year, we can write this as p equals p0 times 1.0216 to the power of t. This is the same as p equals p0 times e to the power of rt, whereas our continuous growth rate. Setting these equal, we get 1.0216 to the power of t equals e to the power of rt, which means 1.0216 equals e to the power of r. Solving for r, we take the natural log of 1.0216, which gives us r equals 0.02137, or about 2.137% per year.
So what does all this tell us about our bird population? Well, since r equals 0.02137 is greater than 0, and lambda equals 1.0216 is greater than 1, we know this population is growing. It's not heading for extinction, it's actually on a path to recovery. If r had been negative, or lambda less than 1, we'd be looking at a declining population that would eventually go extinct. And if r was exactly 0, with lambda equal to 1, we'd have a perfectly stable population. This is the power of the Leslie matrix. It lets us predict the long-term fate of a population from just a few simple rules.
Now, here's the really cool mathematical insight behind all of this. That stable age distribution we found, the 82.06%, 12.05%, 5.9%, that's actually something called an eigenvector of the Leslie matrix. And that growth factor of 1.0216? That's the dominant eigenvalue. Watch what happens when we multiply the Leslie matrix by this special distribution vector. Let me show you. L times V equals, let's calculate the first element, that's 0 times 0.8206 plus 5 times 0.1205 plus 4 times 0.0590, which equals 0.8385. The second element is 0.15 times 0.8206, which is 0.1231. And the third is 0.50 times 0.1205, which is 0.0603. Now if we multiply our vector v by lambda, that's 1.0216 times 0.8206 equals 0.8383, times 0.1205 equals 0.1231, and times 0.0590 equals 0.0603. They're the same. This is the eigenvalue equation, L times V equals lambda times V. This is why the pattern emerges. The matrix has this built-in structure that naturally pushes any starting population toward this stable distribution and this growth rate. This technique isn't just theoretical, it's used every day by conservation biologists around the world. When scientists study endangered species like pandas, elephants, or sea turtles, they use Leslie matrices to figure out whether populations will recover or need intervention. Fisheries managers use them to set sustainable harvest quotas. They need to know how many fish they can catch without causing the population to crash. Agricultural scientists use them to predict pest populations and plan control strategies. Even human demographers use age-structured models to project population trends for policy planning, like predicting how many schools or hospitals a region will need in 20 years. The Leslie matrix has become one of the most important tools in population biology since its introduction in 1945.
One of the most powerful applications is something called sensitivity analysis. We can ask, what if we changed one of our parameters? For example, what if we could increase the survival rate of young birds from 15% to 20% through habitat protection? When we recalculate the eigenvalue with this new Leslie matrix, lambda might jump significantly, let's say to around 1.12, which is 12% annual growth instead of just 2%. That's a huge difference. On the other hand, what if habitat loss or pollution drops that survival rate to only 10%? Lambda might fall below 1, perhaps to 0.95, that's a 5% annual decline that would lead to extinction in just a few decades. This tells conservationists exactly where to focus their efforts. Should we protect nesting sites to boost reproduction? Or is juvenile survival the critical factor that will make or break this species? The sensitivity analysis gives us the answer, and in this case, it shows that young bird survival is the most sensitive parameter. A small change there has a massive impact on the population's future.
Now, I should mention that the basic Leslie matrix does have some limitations, and it's important to understand them. First, it assumes birth and survival rates stay constant over time, which isn't always realistic in nature. A drought year might reduce reproduction, or a disease outbreak might lower survival rates. Second, it doesn't account for density dependence, the fact that when populations get very large, crowding can reduce growth rates through competition for food and space. Third, it ignores environmental variation and randomness. In reality, some years are good, some are bad, and this randomness matters. But here's the good news: scientists have developed extensions to handle all of these complications. There are stochastic Leslie matrices that add random variation to the parameters, better reflecting real-world uncertainty. There are density-dependent models where rates change with population size, incorporating carrying capacity. There are stage-based models, like the Lefkovich matrix, for organisms where age isn't as important as developmental stage. Think plants that can stay as seeds for years, or insects with complex life cycles. The basic Leslie matrix framework is incredibly flexible and has been adapted to handle almost any population structure you can imagine. So let's step back and appreciate what we've accomplished here. We started with what looked like complete chaos, numbers bouncing up and down with no apparent pattern. Year 0 to year 1, young birds jumped from 3,000 to 3,600. Year 1 to year 2, they dropped to 3,130. It seemed random, unpredictable, impossible to forecast. But by organizing just 6 simple rules, 3 birth rates and 3 survival rates, into a Leslie matrix and repeatedly applying it, we uncovered hidden order. We found the stable age distribution that the population naturally gravitates toward: 82% young birds, 12% middle-aged, and 6% old. We discovered the long-term growth rate of 2.16% per year that determines whether the species survives or goes extinct. And we gained a powerful tool that lets us not just predict the future, but also understand which factors matter most for conservation. What seemed like randomness was actually a beautiful mathematical pattern all along, driven by the eigenvalues and eigenvectors of a simple matrix. That's the hidden code of survival, and now you know how to read it. From 6 simple numbers, we can predict the fate of an entire species. That's the power of mathematics applied to the natural world.
The Leslie matrix, developed by P.H. Leslie back in 1945, transformed how we understand population dynamics. It gave us the ability to see through the noise of year-to-year fluctuations and identify the fundamental forces shaping life on Earth.
And the best part? This same mathematical framework can be applied to populations of any age-structured species, from insects to elephants, from fish to forests. The hidden code of survival is universal, and now you have the key to unlock it.